Peter Naur has written one of the most important papers in computer science. It's called Programming as Theory Building. In this paper, Peter refers to the act of programming and the act of building software, and especially its modification, as a consequence of the theory which the original programmers had built in their head. But before we actually get into the paper, I want to tell you a little bit about who is Peter Naur, and once you hear who he is, you will see why we should listen to this guy. Peter Naur is a Danish computer scientist and a Turing Award winner. He is best known as one of the contributors to the Backus-Naur form, which is abbreviated as BNF notation, used in describing the syntax for most programming languages. He also contributed to the creation of the programming language ALGOL 60. If you take John Backus' extreme programming methodology, then you would see that it's rooted, at least some of it is rooted in Peter Naur ideas, and John Backus actually admits it. So this guy has a huge influence on the programming, on programming languages, and on theories behind it. And therefore, if this guy has something to tell us about the maintenance and the creation of softwares and how programmers are dealing with software and how it relates to other areas, then we as admiring ships should listen to this guy. Peter Naur is widely known as one of the authors of the programming language syntax notations, BNF, and in 1985 he presented this work, this research papers, which is titled Programming as Theory Building. In this paper he's tried to understand what's going on in the design and in the coding of the program. How much documentation should you create? And is documentation important? We know that the program itself changes faster than the documentation, so what exactly should be in the documentation and how important it is? Some people claim you don't really need documentation. What is Peter Naur's view on this? He is especially interested in what I'm actually also especially interested in. How do you maintain a program? You have the previous programmers who coded this program, and let's say they are not around anymore. So what is the approach, or how do you maintain such a program? Because as we know, when you build something, let's say you are building the Empire State Building, then you don't really do many changes there. You don't say, oh, I need to take this window and color it with red. Let's move the building to the second street. Let's make it a little shorter because the clouds are like this, and it would be better if it would be horizontally placed and the entrance would be there. Alright, you don't do this with buildings, but with programming and with software packages, you did this all the time. You could actually claim that the whole target of programming, the whole target of what you're doing is to enable this flexibility. So therefore we should handle with care, and we should understand how the paper advises us to work with such things. So in Naur ideas, the designer job, the architect work, is not to pass along the design to the next developer, programmer who is maintaining the software, but to pass along the theory, deriving the design. So it's not that you design something and then you implement it. You build a theory for yourself about the state of the world, about how you model the state of the world in the program. And then based on this theory, you are going to create your design. This is like an empirical thing. This is what's happening. He is only describing it in the paper. He does not claim you should build step a theory, and then you should do a design, and then you should implement. He claims this is what's going in the heads of the people and the programmers. They build some kind of a theory around the state of the matters, and then they build a design, and we should take care a special treatment for this theory, which was placed before the design. And once you understand this point, you understand the whole paper. Because then when you transfer a software to be maintained by other programmers, or you yourself get to maintain a software, the target is to understand the theory that was sitting in the minds of the programmers who created the original design, and not just reading the code, okay? And he actually claims in the paper that you cannot understand this theory just by reading the code or reading the design. It's just impossible. You can get hints into them, but the theory needs to be explicitly referred to. So in this paper, the programming as theory, he claims that what is programming, he asks what programming, and he says that programmers, what they do is they achieve some kind of an insight, a theory into the state of the matters. And this is in contrast to the standard notion that programmers just are a production of programs. They just produce text. Okay, this is the other extreme. But it's not just the production of this button should be here. Okay, so let's write this line of code that places this button here. But it's a theory behind it and the connection. He has a conviction that it's important to have an appropriate understanding of what programming is. And only once we understand what is programming, then only then we could move on and understand how do we maintain programs. So yes, while it's true that programming and the programmer's knowledge is an activity that refers to the real world, and then it's using symbol manipulation, the writing of symbol that is taking place on your monitor in order to create a program. But then a major part of programming is the manipulation and the modification of this existing program. So let's say you have some group A, this is from the paper, right? You have some group A which is building a program to solve some problem. And then comes along group B and decides that for the program they need to do some changes. So what they do is that they communicate with group A. They read the documentation and they get personal advice from group A. Then group B manages to develop the additional features they wanted from the application. The special thing here in this example is that group B actually communicated and got the advices from group A because the group A was there. But then when group C comes along and it tries to manipulate this software, they take the review and the suggestions by group B, but because they are not the original group, then they do not understand really the theory behind the software. They are less close to the theory. And then what they saw is that when they used the software, as the software evolved, then the theory got messed up and lost in the software, and they practically destroyed the power of the software. And the reason for that is that the theory was not self-obvious in the software itself. So they could not understand the small things that were sprinkled here and there, but these small things, this small power that was in the software was like from the theory of the original developers. For example, if you have some special code which does the code generation and some structure of the program, so it's not explicitly stated this is the structure of the program, this is what we meant. Okay, this is structure. So you start building up and you start adding feature, but you deviate from it, not necessarily knowing the full power and the full expectation of group A for this specific section of the code. And therefore, seeing the full program text and the additional documentation is insufficient to get a deeper insight into the design and the theory that was presented actually by group A. The thing is that group B was actually able to communicate with group A, but group C was not able to communicate with group A. So this is true, and this is especially true for large code bases where you have more than 200,000 lines of code, because for small code bases, then you might get along there. So the conclusion seems inescapable that at least with certain kinds of large programs, then the continued adaptation and modification and the correction of errors of them is essentially dependent of a certain kind of knowledge, which is possessed by the group of programmers who were closely and continuously connected with the original group of developers who wrote it. And here he refers to Ryan notion of theory as appears in the example of what Karl Popper has said. And the notion of the theory in more details means that there is a difference between an intelligent activity and intellectual activity. Okay, a person must have in order not only to do certain things intelligently, but also to explain them. When you have the capability to also explain them, this moves ahead into intellectualism and not mere intelligence for doing certain things. So the intellectual activity goes beyond the activity that is merely intelligent. And if the person is building and having a theory, he should have this intellectual activity. So what is exactly this theory? This theory that programmers actually built. It's the theory of how certain affairs of the world will be handled and supported by the computer program. And it transcends all the documentation, and it transcends the code, and it transcends the answer. It's an actual knowledge that the original developers had. And it's not merely the program text. It's some world aspect and activities. And the program text is almost irrelevant to this theory that is created in the mind of the original developers. Its relevant can only be made by someone who understands the whole world and the whole aspect of the programmers. The programmers who have this original theory can explain why each part of the problem is what it is, and support any actual program text with a justification of some sort. They are also able, because they have this theory in their mind, to respond to constructively to any demand for a modification of the program. Even if this may sound clear to you, the problem is that it's not so clear to people outside of the programming industry, which means you are used to building things. You have a production line of cars, so you have also a production line of coded text. You input the specification, you get a good programmer, and he would output the text that would make this program work. But it's not really enough, and as we said, you cannot, usually in standard life cycle, you don't take a car and say, oh, we are going to add a fifth wheel and it's going to run on the side, and instead of batteries, we are going to insert gas, or instead of gas, we are going to insert helium. It's not going like this, but in program, it's going like this, and therefore you need a stable basis, and the stable basis is the theory behind the design. So, if there is a finance guy who thinks that changing the features of the program, the cost is the cost of altering the text of the program, while this may sound very simplistic, then it's not like this. It's a whole process of understanding the theory and getting the program to be changed. And even if you are a programmer, then you can say, okay, the software is flexible. I built the software in a flexible way so that people in the future can easily update it, can easily maintain it. But again, Peter Naur says this is not enough. And remember, Peter Naur is the creator of ALGOL. He's got the award of Turing award, so it's okay. So he's saying that no, it's not enough. You need to somehow communicate the theory behind the application. It's not enough for it to be flexible. And this observation leads to the important conclusion that problems of program modification arise from acting on the assumption that programming consists of programming of text production, instead of recognizing that programming is an activity of theory building. For a program to maintain its quality, it is mandatory that each modification is firmly grounded on the theory behind it. And simplicity is good, structure is good, but it can only be understood in the context of the theory of the program. Now, as for the program life, death, and revivals, there are some situations where it's needed to revive a program from death. Okay, but if the original developers are not there, then it's an extremely almost a situation which is not possible, and again we refer to complex software. So just as with small particles and small scale, the Newton laws hold, so with small softwares they hold, but with large code bases, then this theory building is super important. And such a problem can occur where and arise when a program is not kept continuously alive by a set of team programmers who are the ones who originally developed it and keep the operational burden low. The theory building suggests that if you have a case where you need to, therefore it's a result of the theory building that if you have a case where you need to maintain a large code base, 200,000 lines of code and more, just as a small rule of thumb, then if the original programmers are not there to communicate their theory, then in many cases you had better write a whole new code base. To sum up, accepting program modifications demanded by changing external circumstances to be an essential part of the programming process, then it is argued that the primary aim of programming is to have the programmers build a theory of the way of the matters at hand that may be supported by the execution of the program. Such a view leads to a notion of program life, what depends on the continued support of the program by programmers having its theory. Further on, this view of the notion of the programming method and the understanding of a set of rules of procedures to be followed by the programmer is based on invalid assumptions and so has to be rejected. As further consequences of this view, programmers have to be accorded the status of responsible permanent developers that continuously work on this project. Kent Beck has suggested that it's useful for a design team to simplify the general design of a program to match a single metaphor. The value of a good metaphor increases with the number of designers. The close each person guess is close to the other people's guesses, then the greater the resulting consistency of the final system design. Imagine 10 programmers working as fast as they can in parallel, each making a design decision and adding classes as he or she goes. Each will necessarily develop his own theory as they go. As each adds code, the theory that binds their work becomes less and less coherent and more complicated. Not only maintenance gets harder, but their own work gets harder. This design easily becomes a kludge. If they have a common theory, on the other hand, they add code in ways that fit together. Now, about the documentation. The documentation is almost certainly behind the current state of the program. It's late, but people are good at looking around. What should you put at the documentation? So what should you put inside the documentation? That which helps the next programmer to build an adequate theory of the program. This is so important. The documentation should mainly help the programmer build an adequate theory of the program, be it the history of how decisions were taken, be it videos, be it discussions, be it talks with the client. The theory behind the program is the most important thing in documentation in order to pass this theory building to the next programmers. So, experienced designers often start their documentation with the metaphor, the text describing the purpose of each major component, and the drawing of the major interactions between the major components. And these three items alone take the next team a long way to constructing a useful theory of the design. The source code itself serves to communicate a theory to the next programmer. Simple, consistent naming convention helps the next person to build a coherent theory. When people talk about clean code, a large part of what they are referring to is how easily the reader can build a coherent theory of the system. So documentation cannot and so need not say everything. Its purpose is to help the next programmer build an accurate theory about the complex system.